Hey everyone, welcome back to Chem Story. Today we're diving into something fascinating in organic chemistry, carbocation rearrangements. Have you ever wondered why carbocation ions shift? What makes them rearrange, and how does that affect the reaction outcomes? Let's find out. Carbocation rearrangements come down to one key factor, stability. When a carbocation forms, it doesn't always stay in the same spot. If there's a path to becoming more stable, the molecule will take it. That's exactly what's happening during a carbocation rearrangement. But of course, if rearranging doesn't significantly increase stability, the carbocation simply stays put. Typically, rearrangements only happen when there's a noticeable boost in stability. This stabilization can happen in several ways. For instance, a hydrogen atom, along with its bonding electrons, essentially acting as an H- ion, can shift over to an adjacent carbon, resulting in a more stable carbocation. Similarly, an entire alkyl group can also shift positions for the same reason, stability. And in cyclic molecules, sometimes stability comes from ring expansion, where the ring rearranges itself to relieve strain and form a larger, more stable structure. So here's the bottom line. Carbocations don't choose to rearrange. They're simply responding to internal molecular forces, always moving toward greater stability. Now, let's see how a hydride shift changes the reaction outcome. Imagine we're starting with compound A, 2-bromo-3-methylbutane. If we react this with methanol, we normally expect an SN1 reaction, forming compound B as our final product. Sounds straightforward, right? Well, here's the twist. It doesn't quite turn out as expected. When we actually run this reaction, compound B does form, but surprisingly, it's not the main product. Instead, the major product is something unexpected, compound C. So what's happening here? Let's break this reaction down step by step and figure out exactly what's going on. First, bromine leaves, forming a secondary carbocation, as expected. At this stage, methanol could immediately attack, giving us compound B. But before that happens, there's a twist, a hydride shift. Here's what's going on. A hydrogen from the neighboring carbon shifts over, carrying its bonding electrons. This shift moves the positive charge, converting the secondary carbocation into a much more stable tertiary carbocation. Why does it happen? Simply put, tertiary carbocations are more stable than secondary ones. After this rearrangement, methanol quickly attacks the new, more stable carbocation. Following deprotonation, we end up with compound C as the major product. So what's the key takeaway? Carbocations don't just wait around. And here's the key part. Before the nucleophile even gets a chance, they might rearrange to find greater stability. All right. Now that we've mastered hydride shifts, let's explore another essential rearrangement, alkyl shifts. We'll start with compound D, 3-bromo-2,2-dimethylbutane. Treating it with methanol, you might predict the formation of compounds E and F based on hydride shift logic. But here's the interesting part. Compound F comes from a more stable carbocation intermediate, so we'd naturally expect it to dominate. When we run the actual reaction, the results align perfectly with this prediction. Compound E does form, but only in small amounts. Compound F is clearly the major product. So what's really happening here? Let's break this down step by step and discover exactly why stability is guiding the reaction. First, bromine leaves, creating a secondary carbocation at the initial position. Now, methanol can immediately attack this carbocation, forming a new carbon-oxygen bond. After a quick deprotonation step, we get compound E. But here's the catch. The secondary carbocation isn't the most stable intermediate possible. That's why this pathway doesn't dominate, and compound E forms only in minor amounts. Before methanol even gets a chance to react, the secondary carbocation rearranges. A methyl group from the neighboring carbon shifts over, bringing its bonding electrons along. This shift moves the positive charge onto a more stable tertiary carbon. Now that we've formed the more stable tertiary carbocation, methanol quickly attacks. Finally, after deprotonation, we get compound F as our major product. Again, the driving force here is stability. Tertiary carbocations are significantly more stable than secondary ones. Because of this, the rearrangement happens first, favoring the pathway that leads directly to compound F. Next, let's look at ring expansions, a unique type of carbocation ion rearrangement that results in a larger ring. We start with compound G containing a 5-membered ring. When we treat it with methanol, we typically expect an SN1 reaction. Based on previous examples, compound H might seem like the logical product. So how would that happen? First, bromine leaves, creating a secondary carbocation ion. Then, a neighboring methyl group shifts over, stabilizing the carbocation ion by forming a tertiary center. At this point, methanol attacks, and after deprotonation, we'd get compound H. But is that what we actually see? Surprisingly, compound H isn't the major product. Instead, the major product turns out to be compound I, which features a 6-membered ring instead of a 5-membered one. So, what's really happening here? Let's slow down and break it down step by step. First, bromine leaves, creating a secondary carbocation ion, just like we expected. But before methanol even steps in, something better occurs, a ring expansion via an alkyl shift. Here's what's happening. A carbon-carbon bond inside the 5-membered ring shifts, bringing its bonding electrons along. This rearrangement moves the positive charge, forming a new, more stable tertiary carbocation ion. But stability isn't the only reason for this shift. It also relieves ring strain. 5-membered rings have some strain, while 6-membered rings have nearly ideal bond angles, making them more stable. So naturally, the molecule rearranges to expand its ring before the nucleophile attacks. After this ring expansion, methanol quickly attacks the more stable carbocation ion. Finally, after deprotonation, we end up with compound I as our major product. Here's the key takeaway. Carbocation ions don't just shift positions between neighboring carbons, they can also rearrange rings, leading to more stable structures. Alright, that brings us to the end of our lesson on carbocation ion rearrangements. Thanks for watching, and I'll see you next time.